The second part of our analysis of chlorination of methane will deal with the thermodynamics of this reaction. You've probably heard the concept of thermodynamics before, and thermodynamics is a branch of chemistry which deals with energy changes in chemical and physical transformations. It is particularly relevant to the studies of chemical equilibrium because at that point things are no longer moving, so we're not subject to chemical kinetics at the same time. And in chemical equilibrium, we can say that A plus B converts to C plus B, and the equilibrium constant is defined as C times B over A times B. In the case of methane, this equilibrium constant is very large, methane chlorination. It's about 10 to the 19th, which means that the reaction is essentially reversible, so we don't have any A and B left. Now, the reason why this C and D are formed in such large preference is that they must be more stable, because the system tends to adapt a state of lower energy. And so there must be some relationship between the equilibrium constant and the energy that is liberated during the course of reaction. And indeed, that relationship is that KEQ equals E to the power of minus delta G0 over RT. Delta G here is the Gibbs free energy, T is temperature in degrees Kelvin, and then finally R is the gas constant. Okay. And now the reverse relationship is that delta G, the energy outcome of a reaction, equals minus RT ln KEQ. Now in cases where KEQ is larger than 1, ln of KEQ is going to be larger than 0, which means that the delta G will be lower than 0, which means that the reaction is favorable. The reactions which occur with a negative total energy output are favorable because they release energy. On the other hand, if KEQ is lower than 1, that means that most of our starting materials have not converted into products. That will lead us to ln KEQ being lower than 0, and then delta G being greater than 0, leading to an unfavorable reaction. Now, these delta G values, they don't have to be overly large to drive the reaction all the way to completion. So if we have a delta G of greater than minus 3 kilocalories per mole, that already means that the reaction is 99% done. There's less than 1% starting material. How do we know this? So that's the question. And well, we plug this delta G value into our KEQ equation. So this is E minus delta G over RT. So that is now E minus 3,000 calories per mole. We got to convert this into basic units over 1.99 calories per mole Kelvin, that is the R constant, and times 298 kelvins, which is our room temperature. And that will give us E to the, sorry, this value is negative, E to the 5.06, which is then 157.5, which meaning that is our equilibrium constant is high, and therefore there's very little starting material left. And the question is, well, this delta G is related to KEQ, but are there any components that go into delta G? Is this a single uniform value, or is it composed of something? It turns out that it's not a uniform value, that delta G equals delta H minus T delta F, which means, first of all, it's dependent on temperature, and it's composed of two main parts, delta H part, which is the enthalpy, which is most commonly associated with the heat release or introduced into the reaction, and then delta F is entropy, and entropy correlates to the disorder of the system. Now, of course, delta G, just like delta H and delta F, is basically the delta G, is the G of products minus G of reactant. So it's change of free energy. Okay? Now let's look at the relative contributions of delta H and delta F. And so normally delta H is a much larger contributor, but if we look again at the delta G equals delta H minus T delta S, then we see that the part which is T delta S becomes more and more relevant at higher temperatures. And so while it's safe to, in many cases, ignore pretty much entropy at room temperature, at higher temperature that is no longer a safe conclusion. And so delta H is basically an amount of heat evolved or consumed in the reaction. If delta H is lower than 0, that means that the heat is released. And such processes are called exothermic. If delta H is greater than 0, it means that the heat is consumed, and such processes are known as endothermic. Okay? And how much heat will be released or consumed depends critically on the type of bonds that are broken or formed in the course of the reaction. The change in delta S is basically the change in the disorder of the system, or its randomness. It has a negative sign, minus T delta S, which means that the positive entropy change is favorable. Remember, entropy is a measure of disorder in systems. So if we increase the disorder in the system, that is favorable. But again, as I mentioned previously, delta H is typically much larger than T delta S. If we look at some values for chlorination of methane, just to illustrate this, delta H is minus 25.0 kilocalories per mole, and T delta S at room temperature is minus 0.86 kilocalories per mole. So about 30 times lower. Okay? But again, this is T delta S, so this depends on temperature, so be careful about that. Now, delta H value comes from the bonds that are formed or broken. And this is the critical contribution to our delta H factors. And to break a bond, you need to invest energy. And to form a bond, you don't need to invest energy. Energy is released because bond formation is favorable. And so a bond dissociation energy is basically an energy that is needed to take, let's abbreviate with BDE, so it's needed to take A2 into two atoms of A. So this is a bond dissociation energy of A bond, right? And in order to define a bond dissociation energy, we need to talk about sort of 50-50 breaking of this bond when each one of them takes an electron. And so we get A plus B. This process is described by bond dissociation energy. This is called a homolytic cleavage. Now we've been familiar with the other type of bond breaking where one atom takes everything. And so this would be A minus plus B plus. And BDE, bond dissociation energy, does not apply here. This is very important. If you confuse this, you'll get yourself in a big trouble. And this process is called heterolytic cleavage. So clearly the bond dissociation energy argument can be used to analyze only reactions which break homolytically, right, which is an important point. Okay? And so now we can define our energy outcome of a reaction as delta H reaction being the sum of BDs of broken bonds. And remember, these come with a positive sign because we need energy input. Minus the sum of the BDs of formed bonds. And these come with a minus because energy is released. Okay? Now there is these bond dissociation energies, they vary. Different bonds, they require different energy to be broken. And there is a table in your book which we will give you on an exam, but you should consult to look at these energies and be able to figure out the energy balance of a reaction based on the bond dissociation energies of individual bonds. Now we're going to see how that pans out for chlorination of methane, our case study. So if we look at the bonds that are involved, the bond dissociation energy of methyl hydrogen bond is 104 kilocalories per mole. The bond dissociation energy of chlorine-chlorine bond is 58 kilocalories per mole. The bond dissociation energy of hydrogen-chlorine bond is fairly high, 103. And then the bond dissociation energy of methyl chlorine bond is 84 kilocalories per mole. Now, our initiation step we'll analyze it anyway, but you have to realize that it's fairly relevant in terms of energy balance because it happens only once. The bulk of the reaction energy balance comes from propagation, and very little comes from initiation and termination steps because these are the events that don't happen on a regular basis but only once in a while. But anyway, this bond dissociation energy, this is basically just the bond dissociation energy of chlorine. Obviously energy input is needed, so this is plus 58 kilocalories per mole. And this energy is provided by light, so this is unfavorable. Now the second step is propagation, and remember in propagation step we actually have two sub-steps. So the first one is the reaction of chlorine plus CH4 to give us CH3 plus HCl. Okay? Now here we break the CH3H bond. And so this comes with a price of 104 kilocalories per mole. But on the other hand, we form an HCl bond. And this gives us back 103 kilocalories per mole. So the first step has an overall still negative, still unfavorable balance of plus 1 kilocalorie per mole. But as we mentioned, the propagation is a two-step process. So the second step is CH3 plus Cl2, giving us CH3Cl plus single Cl. And in this case, we break the Cl-Cl bond. And so this comes with a price. But this price is relatively small because this is a weak bond, so it's just 58 kilocalories. On the other hand, we form a carbon-chlorine bond, which turns out to be much stronger. So this is minus 84 kilocalories per mole, leaving us to an overall balance in the second step of minus 26 kilocalories per mole. And then adding the first and the second propagation step, the total propagation energy balance is minus 25 kilocalories per mole. So this is the energy that is released in each propagation step. And this is what drives our reaction. This is what explains why are our products so much more stable than our reactants, and why is accordingly our equilibrium constant so strong, so high, so that the reaction essentially goes to completion. Just for completeness' sake, the termination step, as I mentioned, can occur through a number of different variants, but again, it doesn't matter because first, it happens only once in a while, and secondly, it's typically cancelled out by initiation because each initiation needs one termination to remove that reactant intermediate. And so if we assumed that our termination step is simply recombination of two chlorines to simplify things, then our energy balance here is minus 58 kilocalories per mole because the bond is formed, and this cancels out the initiation. So overall, the propagation energy balance is what is the key to this reaction. In the case of chlorination, propagation energy balance is highly favored. In our next lecture, we will see how different types of reactions have different energy balances that can make them more or less favorable.